the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No mic, no fame, just the sound we crave. Tune and turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. In shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go.
Thanks. I wonder though why the term podcast is used for what I consider a video format. Podcasts are like my time, audio only. I am happy nonetheless to be given the opportunity to speak through this medium. When I first started thinking about numbers that were not integers, which would correspond to the natural numbers, I used the word class to describe such collections of numbers. It became quickly clear to me that I needed a much more precise language to formulate and prove my findings, and I introduced the new idea of set. I was always very interested in the paradoxes that arose in the theory of the natural numbers. For example, the one where you are supposedly listing off all natural numbers from 1 upwards, but at some point you claim you have listed all natural numbers already. This is simply impossible, of course. That's where I became interested in the question of how big the collection of natural numbers really is, because the concept of infinity in itself is not clearly defined and is actually kind of problematic. The set of natural numbers and the set of rational numbers have the same cardinality because there is a simple one-to-one correspondence between them. This means that every natural number can be matched with a unique rational number, and vice versa. For example, you could match the natural number 1 with the rational number 1.1, 2 with 2.1, 3 with 3.1, and so on. This is possible because the rational numbers contain all the natural numbers as well. The proof of the uncountability of the real numbers is often attributed to me, although others have independently arrived at this result. The significance of this discovery is that it showed that the real numbers are much more numerous than the natural numbers. In particular, the real numbers cannot be put into a one-to-one correspondence with the natural numbers, which means they form a larger infinity. This discovery has important implications for many areas of mathematics, as it provides a foundation for understanding the behavior of real valued functions and sequences. A prime number is a positive integer that is greater than 1 and has only two distinct positive divisors, 1 and the number itself. For example, the first six prime numbers are 2, 3, 5, 7, 11, and 13. On the other hand, natural numbers are the numbers used to count objects and represent a set of positive integers starting from 1, 1, 2, 3, 4. Real numbers represent any number that can be represented on a number line and include both rational numbers and irrational numbers such as pi and the square root of 2. Yes, my diagonal argument is often used to demonstrate the uncountability of the real numbers. The argument works by showing that any attempt to enumerate, list all elements of an infinite set, the real numbers between 0 and 1, must fail. The argument works as follows. 1. Assume for the sake of contradiction that we have an enumeration of all real numbers between 0 and 1. 2. Construct a new real number that differs from the nth real number in the enumeration in the nth decimal place. 3. This new number cannot be in the enumeration, contradicting the assumption that the enumeration includes all real numbers between 0 and 1. Therefore, the enumeration cannot exist, and the real numbers between 0 and 1 are uncountable. The important implication of this argument is that the real numbers between 0 and 1 form a larger infinity than the natural numbers. It also highlights the limitations of our attempts to understand and describe infinity. Cardinality is a way of measuring the size of a set by counting the number of elements in the set. It's different from simple size because it applies to both finite and infinite sets, and it allows us to compare the sizes of infinite sets. For example, the set of natural numbers and the set of integers have the same cardinality, which is also the same cardinality as the set of rational numbers, even though the set of integers contains infinitely many more elements than the set of natural numbers. This is because we can establish a one-to-one correspondence between the two. My claim was called Cantor's theorem, named after me. This theorem states that for any set S dollars, the power set of S dollar, E, the set of all subsets of S nus, has a larger cardinality than S dollars. This is a consequence of the fact that the power set of an infinite set is always strictly larger than the set itself. The significance of this theorem is that it highlights the limitation of our intuition about infinity. It implies that there is no set whose cardinality lies strictly between that of the integers, or any countably infinite set, and that of the real numbers. I introduced the Aleph numbers as a way to categorize the different sizes of infinity. The Aleph null, denoted as 0, represents the cardinality of the natural numbers, and it is the smallest infinite cardinality. Similarly, the Aleph numbers Noan, etc., represent increasingly larger infinite cardinalities. By using the Aleph symbols, mathematicians have been able to classify and study different orders of infinity in a more systematic and rigorous manner. The proof of my theorem is known as a proof by contradiction. Essentially, the argument goes as follows. 1. Assume, for the sake of contradiction, that there exists a set S dollars such that its power set, denoted by halves, has the same cardinality as S. 2. Using the axiom of choice, which is a fundamental axiom of set theory and is equivalent to the well-ordering principle, construct a bijection, a one-to-one correspondence from S dollars to S. 3. From this bijection, it follows that elements in S dollars are mapped to sets and sets in R dollars are mapped to elements. This contradicts the definition of a set. 4. Therefore, the assumption that there exists a set with a power set of the same cardinality leads to a contradiction, and the theorem is proved. This result has profound implications for set theory and the study of infinity. It highlights the counterintuitive nature of infinity and shows that some infinities are larger than others. Ordinal numbers, also known as transfinite ordinals, are used to describe the order type of well-ordered sets. They are used to describe the position of an element in a well-ordered sequence. Some basic ordinal numbers are 0, 1, 2, 3, etc., but the ordinal numbers can be extended to infinity and beyond. The distinction between ordinal numbers and cardinals is that ordinal numbers capture the order relationship in a well-ordered set, while cardinal numbers only capture the size of a set, regardless of order. You may be referring to the paradoxes that arise from Russell's paradox, which was discovered by the philosopher and mathematician Bertrand Russell. This paradox exposed a contradiction in the standard axioms of set theory at the time. To address this paradox and others like it, mathematicians reformulated the axioms of set theory using the language of first-order logic. This allowed them to avoid the paradoxes by explicitly excluding certain constructions, such as the set that contains all sets that do not contain themselves. This reformulated set theory is now known as Zermelo-Fraenkel set theory or ZF set theory. One reason is that my work challenged the prevailing intuition in mathematics about infinity. Many mathematicians at the time believed that only finite objects could be accurately described by mathematics, and they rejected the idea of infinitely large objects or transfinite constructions. Kronecker's resistance to my work was also influenced by his belief that mathematics should only be concerned with concrete, realizable objects. He argued that the language of transfinite numbers had no physical meaning and was therefore meaningless. Hilbert's thought experiment, also known as the Hilbert Hotel paradox, is a popular way to illustrate the counterintuitive aspects of infinity. The idea is that a hypothetical hotel with infinitely many rooms, where each room is currently occupied, can always accommodate infinitely more new guests. This illustrates the idea that the number of integers is strictly smaller than the number of real numbers, even though both are infinite. It's a fun and intuitive way to think about infinity in terms of hotel rooms rather than abstract mathematical constructions. To explain the difference between array finite and infinite sets to a student who is not familiar with my work, I would suggest the following analogy. Imagine a set of numbers as a row of seats in a theater. An array finite set would be like a row with a finite number of seats, say 10. You can count each seat and know exactly how many there are. You can also assign each seat a unique number 1 to 10. On the other hand, an infinite set would be like a row of seats that goes on infinitely in both directions. When I first began working on my ideas about transfinite numbers, I was focused on the foundational questions of mathematics rather than the applications. However, I did recognize the importance of rigor in mathematical analysis, and I thought my work could help to refine and make more precise the way mathematicians thought about infinity. It was not until later that I saw the specific impact of my work on real analysis and other areas of mathematics that rely on the precise definition of real numbers and the topology of the real line. When I first developed the theory of transfinite numbers, I was focused on addressing mathematical problems and resolving foundational issues within mathematics itself. However, I did recognize the potential for my work to have applications in other areas of study, such as the natural sciences. For example, set theory can be used to model and analyze complex systems in biology, such as populations of organisms and ecological networks. Additionally, set theory has been applied in computer science to the study of algorithms, data structures, and computability theory. My religious beliefs as a devout Christian influenced my understanding of infinity and the absolute infinite in several ways. First, I saw mathematical infinity as a reflection of the infinite nature of God. Just as the infinite set of natural numbers never ends, so too does the love and wisdom of God know no bounds. Additionally, my work on transfinite numbers allowed me to explore the idea of infinity beyond the strict logic of mathematics. For example, the idea of the cardinality of the power set of the natural numbers being larger than the set itself suggests the possibility of limits to our human understanding of infinity. When I was working on my ideas about set theory and transfinite numbers, I was aware that my work was controversial and not widely accepted by the mathematical community. As a result, I was meticulous in ensuring that my proofs were rigorous and clear. For each of my results, I provided detailed and step-by-step argumentation, explaining every step and how it was justified given the existing axioms. I also double-checked all of my proofs and sought feedback from other mathematicians to make sure that there were no logical errors or gaps in my reasoning. Yes, I see parallels between the infinite structures in mathematics and the infinite possibilities in language. Just as there are various mathematical systems, such as the real numbers, integers, and natural numbers, which are all mathematically infinite, language consists of an infinite number of words and combinations of words, allowing for endless possibilities of expression. However, I would say that the infinite structures in mathematics are more rigorous and precise than the endless possibilities of language, as they follow specific and well-defined rules and logic. The development of precise mathematical symbols was crucial to my work, as it allowed me to express abstract concepts and relationships in a clear and concise manner. In a sense, the development of mathematical symbols can be seen as a form of linguistic evolution, as it allowed me to create a new language that could express concepts that had previously been difficult to articulate. However, it is important to note that mathematical symbols are not the same as natural language, as they have a specific set of meaning and rules that everyone in the mathematical community understands and agrees upon. The German language and its academic style had a significant influence on the way I communicated my ideas. The German language is known for its precision and elegance, which is reflected in the way mathematical concepts and ideas are named and expressed. For example, German mathematicians coined the term transfinite numbers and cardinality to describe the objects I was studying. Additionally, the German academic tradition emphasizes formality and rigor in writing, which I adopted in my own writings. This formality is evident in my meticulous attention to detail and my clear and organized presentation of complex mathematical ideas. Yes, I found studying mathematical texts in multiple languages valuable. By reading works in different languages, I gained new perspectives on mathematics and discovered different approaches to problem solving. For example, I was particularly interested in the works of French mathematicians such as Joseph Louis Lagrange and Évariste Galois, as they often took quite different approaches to problem solving than German mathematicians. Reading their works in their original language helped me to appreciate the nuances of their ideas and understand the cultural and historical context in which they were developed. I ensured clarity in my correspondence with other mathematicians by using precise and well-chosen language, and by clearly stating my ideas and arguments. In my letters to Richard Dedekind, for example, I used mathematical symbols and terminology to precisely express the concepts I was discussing, and I provided detailed explanations of my proofs and results. Furthermore, I often included diagrams and examples in my letters to help clarify my points and make sure that my ideas were understood. Additionally, I asked questions and sought feedback from my correspondents to ensure that any misunderstandings were quickly resolved. Yes, studying the language of historical mathematicians like Euclid and Leibniz influenced my work. Euclid's Elements is an important work in the development of axiomatic reasoning, and I studied it carefully to understand the foundations of geometry. Leibniz's philosophical and mathematical writings also had a significant impact on my thinking. He was one of the foremost thinkers of the Enlightenment, and his work on calculus and logic greatly influenced the development of mathematical thought in the 17th and 18th centuries. Yes, I do view mathematical notation as a universal language, as it allows mathematicians around the world to communicate mathematical concepts and ideas effectively, regardless of their native language. The language of mathematics is precise and well defined, and it is based on a set of symbols and rules that are universally understood and accepted by all mathematicians. In contrast, natural language is inherently ambiguous and subject to cultural and linguistic differences, which can make it difficult to communicate mathematical ideas effectively. While natural language can be used to describe mathematical concepts, it is generally less precise and prone to misinterpretation than mathematical notation. As a mathematician, I found it easier to describe concrete mathematical objects, such as integers and real numbers, linguistically, as these objects have tangible and well-defined properties that can be easily described in natural language. On the other hand, describing abstract mathematical objects such as infinite sets and transfinite ordinals can be more challenging, as these objects do not have physical analogues and their properties can be less intuitive. However, with careful use of language and mathematical symbolism, it is possible to describe these objects in a precise and clear manner. I am pleased to see that my mathematical terms, such as transfinite numbers and Cantor's diagonal argument, have entered the lexicon of modern mathematics and have become widely known and used. This indicates the significance and lasting impact of my contributions to the field of mathematics, and it reflects the fact that my work has been foundational to the development of modern set theory and analysis. I hope that future generations will take from my contributions to mathematics an appreciation for the importance of precision and clear communication in the study of mathematics. I hope that they will also recognize the value of exploring foundational questions and the importance of developing new concepts and methods to address them. Furthermore, I hope that my work on transfinite numbers and the continuum will continue to inspire and inform the work of future mathematicians, leading to new insights and breakthroughs in our understanding of infinity and the real line. My work is based on both semantic logic and syntax, as I was concerned with both the meaning of mathematical statements and the correct manipulation of mathematical symbols. However, I think that my work was primarily focused on the semantic aspect of mathematics, as I was interested in the conceptual content of mathematical statements and their relationship to reality. In addition, I believe that the unification of semantic logic, syntax, and conceptual pragmatics is possible, and that a comprehensive understanding of mathematics requires an integration of these different approaches and perspectives. Your questions were well prepared and thoughtful, and they allowed for a deep exploration of my work and ideas on mathematics. I appreciate the time and effort you put into preparing them, and I found our conversation to be informative and enjoyable.
Mics on the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No light, no fame, just the sound we crave. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Hidden in shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go. Pure and raw. Pure and raw. Silence break, raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel.